Portable Network Graphics. Portable Network Graphics, PNG, officially pronounced ping, more commonly pronounced PNG, is a raster graphics file format that supports lossless data compression. PNG was developed as an improved, non-patented replacement for graphics interchange format GIF. If you call it GIF, we're going to have to fight. PNG supports palette-based images with palettes of 24-bit RGB or 32-bit RGBA colors, grayscale images with or without alpha channel for transparency, and full-color, non-palette-based RGB or RGBA images. The PNG working group designed the format for transferring images on the internet, not for professional quality print graphics. Therefore, non-RGB color spaces such as CM, YK are not supported. A PNG file contains a single image in an extensible structure of chunks, encoding the basic pixels and other information such as textual comments and integrity checks, documented in RFC 2083. PNG files use the extension PNG or lowercase png and are assigned MIME media type image/PNG. PNG was published as Informational RFC 2083 in March 1997 and as an ISO/IEC 15948 standard in 2004. Contents: 1. History and development. 2. PNG working group. 3. File format. 3.1 file header. 3.2 chunks with the file. 3.2.1 critical chunks. 3.2.2 ancillary chunks. 3.3 pixel format. 3.4 transparency of image. 3.5 compression. 3.5.1 filtering. 3.6 interlacing. 3.7 animation. 3.8 examples. 4. Advantages. 5. Comparison with other file formats. 5.1. Graphics interchange format. GIF. 5.2. JPEG. 5.3. JPEG-LS. 5.4. TIFF. 6. Software support. 6.1. Bitmap graphics editor support for PNG. 6.2. Web browser support for PNG. 6.3. Operating system support for PNG icons. 7. File size and optimization software. 7.1. Compared to GIF. 7.2 file size factors, 7.2.1 lossy PNG compression, 7.3 image editing software, 7.4 optimizing tools, 7.4.1 tool list, 7.4.2 ancillary chunk removal, 7.4.3 filter optimization, 7.4.4 deflate optimization, 7.5 icon optimization, 8 see also, 9 notes, 10 references, 11 further reading, 12 external links. History and development. See also graphics interchange format, section Unisys, and LZW patent enforcement. The motivation for creating the PNG format was the realization in early 1995 that the Lempel-Ziv-Welch LZW data compression algorithm used in the graphics interchange format GIF format was patented by Unisys. There was also other problems with the GIF format that made a replacement desirable, notably its limit of 256 colors at the time when computers with far more advanced displays were becoming common. A January 1995 precursory discussion thread on the Usenet newsgroup comp.graphics with the subject Thoughts on a GIF Replacement File Format had many propositions which would later be part of the PNG file format. In that thread, Oliver Fromm, author of the popular JPEG viewer QPEG, proposed the PING name, eventually becoming PNG, a recursive acronym meaning PING is not GIF, and also the .png extension. Although GIF allows for animation, it was decided that PNG should be a single image format. In 2001, the developers of PNG published the Multiple Image Network Graphics (MNG) format. With support for animation, MNG achieved moderate application support, but not enough among mainstream web browsers, and no usage among website designers or publishers. In 2008, certain Mozilla developers published the Animated Portable Networks Graphics APNG format with similar goals. APNG is a format that is natively supported by Gecko and Presto-based web browsers and is also commonly used for thumbnails on Sony's PlayStation Portable System using the normal PNG file extension. However, as of 2017, usage of PNG remains minimal despite being supported by all major browsers but Microsoft Edge. 1 October 1996, version 1.0 of the PNG specification was released and later appeared as RFC 2083. It became a W3C recommendation on 1 October 1996. 31 December 1998, version 1.1 with some small changes and the addition of 3 new chunks was released. 11 August 1999, version 1.2 adding 1 extra chunk was released. 10 November 2003, PNG became an international standard ISO/IEC 15948 2003. This version of PNG differs only slightly from version 1.2 and adds no new chunks. 3 March 2004, ISO/IEC 15948:2004. PNG Working Group. The original PNG specification was authored by an ad hoc group of computer graphics experts and enthusiasts. Discussion and decisions about the format were conducted by email. The original authors listed on RFC 2083 are Editor, and by the way, I'm not going to pronounce these names, so I'm just going to spell them out because it's way too much work to figure out how to pronounce all of these names correctly. So, Editor, THOMAS, space BOUTELL. Contributing Editor, TOM, space LANE. Authors, in alphabetical order, by last name, MARK, space ADLER, comma, THOMAS, space BOUTELL, comma, CHRISTIAN, space BRUNSCHEN, comma, ADAM, space M dot, space COSTELLO, comma, LEE, space DANIEL, space CROCKER, comma, ANDREAS, space DILGER, comma, OLIVER, space FROMME, comma, JEAN-LOUP, space GAILLY, comma, CHRIS, space HERBORTH, comma, ALEKS, space JAKULIN, comma, NEAL, space KETTLER, comma, TOM, space LANE, comma, ALEXANDER, space LEHMANN, comma, CHRIS, space LILLEY, comma, DAVE, space MARTINDALE, comma, OWEN, space MORTENSEN, comma, KEITH, space S dot PICKENS, comma, ROBERT, space P dot, space POOLE, comma, space GLENN, space RANDERS, comma, or not comma, dash PEHRSON, comma, GREG, space ROELOFS, comma, WILLEM, space VAN, space SCHAIK, comma, GUY SCHALNAT, comma, PAUL, space SCHMIDT, comma, TIM, space WEGNER, comma, JEREMY, space WOHL. File format. File header. A PNG file starts with an 8-byte signature, referred to hex editor image on the right. Values and purpose. So we have two columns. Value 89 has the high bit set to detect transmission systems that do not support 8-bit data and to reduce the chance that a text file is mistakenly interpreted as a PNG or vice versa. 54E47. In ASCII, the letters PNG, allowing a person to identify the format easily if it is viewed in a text editor. 0D and 0A, a DOS-style line ending, CRLF, to detect DOS-Unix line ending conversion of the data. 1A, a byte that stops display of the file under DOS when the command type has been used, the end of file character. 0A, a Unix-style line ending, LF, to detect Unix-DOS line ending conversion. Chunks within the file. After the header comes a series of chunks, each of which conveys certain information about the image. Chunks declare themselves as critical or ancillary, and a program encountering an ancillary chunk that it does not understand can safely ignore it. This chunk-based storage layer structure, similar to the concept of a container format or to Amiga's IFF, is designed to allow the PNG format to be extended while maintaining compatibility with older versions. It provides forward compatibility, and this same file structure, with different signature and chunks, is used in the associated MNG, JNG, and APNG formats. A chunk consists of 4 parts: length, 4 bytes, big endian; chunk type/name, 4 bytes; chunk data, length bytes; and CRC, cyclic redundancy code/checksum, 4 bytes. The CRC is a network-byte-order, CRC-32, computed over the chunk type and chunk data, but not the length. We have a table with the columns length, chunk type, chunk data, and CRC. Length, 4 bytes, chunk type, 4 bytes, chunk data, length, number of bytes, CRC, 4 bytes. Chunk types are given a 4-letter case-sensitive ASCII type/name. Compare 4CC. The case of the different letters in the name, bit 5 of the numeric value of the character, is a bit field that provides the decoder with some information on the nature of the chunk it does not recognize. The case of the first letter indicates whether the chunk is critical or not. If the first letter is uppercase, the chunk is critical. If not, the chunk is ancillary. Critical chunks contain information that is necessary to read the file. If a decoder encounters a critical chunk it does not recognize, it must abort reading the file or supply the user with an appropriate warning. The case of the second letter indicates whether the chunk is public, either in the specification or the registry of special purpose public chunks, or private, not standardized. Uppercase is public and lowercase is private. This ensures that public and private chunk names can never conflict with each other, although 2 private chunk names could conflict. The third letter must be uppercase to conform to the PNG specification. It is reserved for future expansion. Decoders should treat a chunk with a lowercase third letter the same as any other unrecognized chunk. The case of the fourth letter indicates whether the chunk is safe to copy by editors that do not recognize it. If lowercase, the chunk may be safely copied regardless of the extent of modifications to the file. If uppercase, it may only be copied if the modifications have not touched any critical chunks. Critical chunks. A decoder must be able to interpret critical chunks to read and render a PNG file. Bullet point IHDR must be the first chunk. It contains, in this order, the image width 4 bytes, height 4 bytes, bit depth 1 byte, comma, values 1, 2, 4, 8, or 16. Color type 1 byte values 0, 2, 3, 4, or 6. Compression method 1 byte, value 0. Filter method 1 byte, value 0. And interlace method 1 byte, values 0 for no interlace, or 1 for Atom7 interlace. 13 data bytes in total. As stated in the World Wide Web Consortium, bit depth is defined as the number of bits per sample or per palette index, not per pixel. PLTE contains the palette, a list of colors. IDAT contains the image, which may be split among multiple IDAT chunks. Such splitting increases file size slightly, but makes it possible to generate a PNG in a streaming manner. The IDAT chunk contains the actual image data, which is the output stream of the compression algorithm. IEND marks the image end. The data field of the IEND chunk has 0 bytes / is empty. The PLTE chunk is essentially for color type 3, indexed color. It is optional for color types 2 and 6, true color and true color with alpha, and it must not appear for color types 0 and 4, grayscale and grayscale with alpha. Ancillary chunks. Other image attributes that can be stored in PNG files include gamma values, background color, and textual metadata information. PNG also supports color management through the inclusion of ICC color space profiles. Unless otherwise stated, all of these ancillary chunks to follow start with a lowercase first letter and then 3 more letters that are all capitals. For example, BKGD is a lowercase b, capital K, capital G, capital D. That is the format for most of these. If it is other than that, I will specifically say so. BKGD gives the default background color. It is intended for use when there is no better choice available, such as in standalone image viewers, but not web browsers. See below for more details. CHRM gives the chromacity coordinates of the display primaries and white point. DSIG is for storing digital signatures. EXIF stores EXIF metadata. This chunk has a slightly different naming convention. It is a lowercase e, capital X, capital I, lowercase f. So the middle 2 letters are uppercase and the outer letters are lowercase. So that is EXIF. EXIF. Gamma specifies gamma. The gamma chunk contains only 4 bytes and its value represents the gamma value multiplied by 100,000. For example, the gamma value 1 divided by 3.4 calculates 29,411.7647059, open paren, 1 divided by 3.4, close paren, multiplied by, open paren, 100,000, close paren, and is converted to an integer, open paren, 29412, close paren, for storage. That is 29,412 for storage. HIST can store the histogram or total amount of each color in the image. ICCP is an ICC color profile. ITXT contains a keyword and UTF-8 text with encodings for possible compression and translations marked with language tag. The Extensible Metadata Platform, XMP, uses this chunk with a keyword, in quotations here, xml:/com.adobe.xmp, and that is the end of the quotation. Note that this chunk starts with a lowercase I, capital T, capital X, lowercase t. So the center two letters are capital and the outers are lowercase, and that is ITXT. PHYS holds the intended pixel size or pixel aspect ratio. The PHYS contains pixels per unit, comma, x-axis, close quotation, 4 bytes. Open quotation, pixels per unit, comma, y-axis, close quotes, 4 bytes, comma, and open quote, unit specifier, close quote, 1 byte, for a total of 9 bytes. So let's say that again without awkwardly saying where the quotes are. PHYS holds the intended pixel size or pixel aspect ratio. The PHYS contains pixels per unit x-axis, 4 bytes, pixels per unit y-axis, 4 bytes, and unit specifier, 1 byte, for a total of 9 bytes. This chunk has lowercase letters on the outside and uppercase letters on the middle, so it is lowercase p, capital H, capital Y, lowercase s. That is PHYS, and that holds the intended pixel size. S-bit, significant bits, indicates the color accuracy of the source data. SPLT suggests a palette to use if the full range of colors is unavailable. sRGB indicates the standard sRGB color space is used. The sRGB chunk contains only 1 byte, which is used for rendering intent. 4 values, 0, 1, 2, and 3, are defined for rendering intent. STER, stereo image indicator chunk for stereoscopic images. TEXT, this chunk is different in naming convention. Lowercase t, capital E, capital X, lowercase t. So once again, capitals in the middle, lowercase on the outside. Text can store text that can be represented in ISO/IEC 8859-1 with 1 key value pair for each chunk. The key must be between 1 and 79 characters long. Separator is a null character. The value can be of any length, including 0 up to the maximum permissible chunk size minus the length of the keyword and separator. Neither key nor value can contain a null character. Leading or trailing spaces are also disallowed. Time stores the time that the image was last changed. TRNS contains transparency information. For indexed images, it stores alpha channel values for 1 or more palette entries. For true color and grayscale images, it stores a single pixel value that is to be rendered as fully transparent. ZTXT. This also breaks convention. It is lowercase z, capital T, capital X, lowercase t. So there are capitals in the middle and lowercases on the outside. Lowercase z, capital T, capital X, lowercase t, z, t, x, t. Contains compressed text and compression method marker with the same limits as TEXT, lowercase t, capital E, capital X, lowercase t. The lowercase first letter in these chunks indicates that they are not needed for the PNG specification. The lowercase last letter in some chunks indicates that they are safe to copy even if the application concerned does not understand them. Pixel format. Pixels in PNG images are numbers that may be either indices of sample data in the palette or the sample data itself. The palette is a separate table contained in the PLTE chunk. Sample data for a single pixel consists of a tuple of between 1 and 4 numbers. Whether the pixel data represents palette indices or explicit sample values, comma, the numbers are referred to as channels, and every number in the image is encoded with an identical format. PNG color type table. Aside. Diagram on the right side. 4 columns, color type, channels, and bits per channel. We will go over the different rows. We have 5 rows: indexed, grayscale, grayscale and alpha, true color, and alpha. First row of data, the color type is indexed. It has 1 channel, and the bits per channel are 1, 2, 4, or 8, and 16 is not an option. For the color type grayscale, we have 1 channel, and the bits per channel are 1, 2, 4, 8, and 16. So all possible channels as shown in the diagram, because the bits per channel are either 1, 2, 4, 8, or 16. The third row of data, color type grayscale and alpha, there are 2 channels, and the bits per channel that are available are either 16 or 32. The fourth row, color type true color, has 3 channels. The bits per channel options are either 24 bits or 48 bits. The last row of data, the 5th row, color type true color and alpha, has 4 channels, and the bits per channel options we have are 32 bits or 64 bits. The permitted formats encode each number as an unsigned integer value using a fixed number of bits, referred to in the PNG specification as the bit depth. Notice that this is not the same as color depth, which is commonly used to refer to the total number of bits in each pixel, not each channel. The permitted bit depths are summarized in the table along with the total number of bits used for each pixel. The number of channels depends on whether the image is grayscale or color and whether it has an alpha channel. PNG allows the following combination of channels, called the color type. 0 in parentheses 000 base 2, in other words, binary 000, grayscale. 2 within parentheses 010 base 2, in other words, binary 010, red, green, and blue, RGB/true color. 3 within parentheses 011 base 2, in other words, binary 011, indexed, channel containing indices into a palette of colors. 4 within parentheses 100 base 2, in other words, binary 100, grayscale and alpha, level of opacity for each pixel. 6 within parentheses 110 base 2, in other words, 110 binary, red, green, blue, and alpha, in other words, RGBA. The color type is specified as an 8-bit value, however only the low 3 bits are used, and even then, only the 5 combinations listed above are permitted. So long as the color type is valid, it can be considered as a bit field and summarized in the adjacent table. Bit value 1. The image data stores palette indices. This is only valid in combination with bit value 2. Bit value 2. The image samples contain 3 channels of data encoding trichromatic colors. Otherwise, the image samples contain 1 channel of data encoding relative luminance. The table to the right is labeled PNG color types. It has 4 columns: color type name, binary, and masks. The binary column has 4 subdivisions, or 4 subcolumns. There is a blank column, and then columns labeled A, C, and P. So let's go through them one row at a time. We have color type 0 named grayscale, and all the binary values are 0. Oh, and there's a last column, masks, and there's nothing in that entry for this row. Color type 2 is named true color, And within our binary table, only the C column is checked here, or the C column bit is turned on. And the masks are color. Color type 3, indexed. In the binary table, the C and P bits are set, and the masks are color and palette. Color type 4, name, grayscale, and alpha. Within the binary columns, the A column is checked, or the 1 bit is set. The masks are alpha. The final entry, color type 6, true color and alpha. Within the binary columns, or the binary columns, we have A and C bits set, and the masks are alpha and color. Bit value 4, the image samples also contains an alpha channel expressed as a linear measure of the opacity of the pixel. This is not valid in combination with bit value 1. With indexed color images, the palette always stores trichromatic colors at a depth of 8 bits per channel, 24 bits per palette entry. Additionally, an optional list of 8-bit alpha values for the palette entries may be included. If not included, or if shorter than the palette, the remaining palette entries are assumed to be opaque. The palette must not have more entries than the image bit depth allows for, but it may have fewer. For example, if an image with 8 bits only uses 90 colors, then it does not need palette entries for all 256 colors. The palette must contain entries for all the pixel values present in the image. The standard allows indexed color PNGs to have 1, 2, 4, or 8 bits per pixel. Grayscale images with no alpha channel may have 1, 2, 4, 8, or 16 bits per pixel. Everything else uses a bit depth per channel of either 8 or 16. The combinations this allows are given in the table above. The standard requires that decoders can read all supported color formats, but many image editors can only produce a small subset of them. Transparency of image. PNG offers a variety of transparency options. With true color and grayscale images, either a single pixel value can be declared as transparent, or an alpha channel can be added, enabling any percentage of partial transparency to be used. For paletted images, alpha values can be added to palette entries. The number of such values stored may be less than the total number of palette entries, in which case the remaining entries are considered fully opaque. The scanning of pixel values for binary transparency is supposed to be performed before any color reduction to avoid pixels becoming unintentionally transparent. This is most likely to pose an issue for systems that can decode 16 bits per channel images, as required for compliance with the specification, but only output 8 bits per channel, the norm for all but the highest end systems. Alpha storage can be associated, within parentheses pre-multiplied, or unassociated, but PNG standardized on unassociated, within parentheses non-pre-multiplied alpha, which means that imagery is not alpha encoded. The emissions represented in RGB are not the emissions at the pixel level. This means that the over operation will multiply the RGB emissions by the alpha and cannot represent emission and occlusion properly. Compression. PNG uses a two-stage compression process. Bullet point pre-compression, filtering, within parentheses prediction. Bullet point compression, deflate, all capitals. PNG uses deflate, all capitals, a non-patented lossless data compression algorithm involving a combination of LZ77 and Huffman coding. Permissively licensed deflate implementations, such as zlib, are widely available. Compared to formats with lossy compression, such as JPG, choosing a compression setting higher than average delays processing but often does not result in a significantly smaller file size. Filtering. Before deflate is applied, the data is transformed via a prediction method. A single filter method is used for the entire image, while for each image line, a filter type is chosen to transform the data to make it more efficiently compressible. The filter type used for a scan line is prepended to the scan line to enable inline decompression. Diagram to the right, we have some pixels labeled CBD on the top, and then below that we have pixels A, X, and then a blank pixel. Beneath the diagram, there is a title or description. It says, PNG's filter method 0 use the data in pixels A, B, and C to predict the value for X. So I don't know why there is D in the diagram because it does not mention anything about D. There is only one filter method in the current PNG specification, denoted method 0, and thus in practice the only choice is which filter type to apply to each line. For this method, the filter predicts the value of each pixel based on the values of previous neighboring pixels and subtracts the predicted color of the pixel from the actual value, as in DPCM. An image line filtered in this way is often more compressible than the raw image line would be, especially if similar to the line above, since the differences from prediction will generally be clustered around 0 rather than spread over all possible image values. This is particularly important in relating separate rows, since deflate has no understanding that the image is a 2D entity and instead just sees the image data as a stream of bytes. In other words, LZW is kind of like compression for a text file, and it just sees a 1D line of data, and therefore this pre-filtering process will help compress some of the 2D aspects of the image before we compress a 1D data stream. Looking at the diagram on the right, we have two bands of color. One is going from a violet or magenta to a cyan, and the next color band is going from a green to a red. The description below: a PNG with 256 colors, which is only 251 bytes large with pre-filter. The same image as a GIF would be more than 13 times larger. And that's because these pre-filters are relating the different rows of data and effectively compressing it so that the LZW just has to worry about the single color band for the most part. There are 5 filter types for filter method 0. Each type predicts the value of each byte of the image data before filtering, based on the corresponding byte of the pixel to the left, A, the pixel above, B, and the pixel above and to the left, C, or some combination thereof, and encodes the difference between the predicted value and the actual value. Filters are applied to byte values, not pixels. Pixel values may be 1 or 2 bytes, or several values per byte, but never cross byte boundaries. The filter types are: diagram, 3 columns, type byte, filter name, predicted value, 5 rows of data, 0 through 4 for the type byte. Going through them in order: type byte 0, filter name none, predicted value 0, so that the raw byte type value passes through unaltered. Type byte 1, filter name sub, predicted value byte A to the left. Type byte 2, filter name up, predicted value byte B above. Type byte 3, filter name average, predicted value mean of bytes A and B rounded down. Byte type 4, path, predicted value A, B, or C, whichever is closest to P equals A plus B minus C. So it's kind of like an average, because I had to think about it, and I was like, okay, well, if A, B, and C are all 50, A plus B is 100, and then minus 50, we get back to 50. So path is just a different kind of average as far as I'm concerned. And that is the end of the table. Alright, so I've done some thinking about correct pronunciation of names, and I think it's really not that important to correctly pronounce the names, to understand PNG format. The only thing correctly pronouncing names is going to do for you is make it so, grammar Nazis don't say, oh my god, they can't properly pronounce this word, I guess they don't know anything about it. What? You say coupling? It's coupling. Oh, you're a fool. I guess you've never, made a loosely coupled system, by passing around function pointers or using virtual functions, because obviously you can't do that because you can't pronounce it. So therefore you have absolutely no coding ability because, obviously the first step to learning how to code well is being able to pronounce things correctly. And if you can't pronounce them, then obviously how could you possibly write a for loop if you pronounce four, right? Like you can't. It's just impossible. Okay. The Paeth filter is based on an algorithm by Alan W. Paeth. Compared to versions of DPCM used in lossless JPEG, and to the discrete wavelet transform using 1x2, 2x1, or for the Paeth predictor, 2x2 windows and HAR wavelets. Comparison is further improved by choosing filter types adaptively on a line-by-line basis. This improvement, and a heuristic method for implementing it commonly used by PNG writing software, were created by Lee Daniel Crocker, who tested the methods on many images during the creation of the format. The choice of filter is a component of the file size optimization, as discussed below. If interlacing is used, each stage of the interlacing is filtered separately, meaning that the image can be progressively rendered as each stage is received. However, interlacing generally makes compression less effective. So from looking at that diagram, it kind of makes sense why interlacing would make compression less effective, because all of your chunks have these pixels that are going to be less related, right? Because the pixels that are right next to each other are going to more closely match in an image usually than pixels that are further away. Interlacing. PNG offers an optional two-dimensional, 7-pass interlacing scheme, the Atom7 algorithm. This is more sophisticated than GIF's one-dimensional 4-pass scheme and allows a clearer, low-resolution image to be visible earlier in the transfer, particularly if interpolation algorithms such as bicubic interpolation are used. However, the 7-pass scheme tends to reduce the data's compressibility more than simpler schemes. The fastest code to write is the code you don't write at all, and I'm going to say this interlacing stuff, it made sense in the time when internet was slow, but this seems like a completely unnecessary feature. And if I can get a working, usable library that omits this interlacing feature, I will be perfectly fine with that. Even if it means that, certain old PNG files or PNG files with interlacing just don't work, because they don't even compress as well. And now I gotta write all this extra code to generate this weird pattern. The pattern's cool, but I think it's just a whole bunch of extra work that's not going to actually give me any extra value for the things I need to do with a PNG file. Animation. PNG itself does not support animation. MNG is an extension to PNG that does. It was designed by members of the PNG group. MNG shares PNG's basic structure in chunks, but it is significantly more complex and has a different file structure, which automatically renders it incompatible with standard PNG decoders. The complexity of MNG led to the proposal of a PNG by developers of the Mozilla Foundation. It is based on PNG, supports animation, and is simpler than MNG. A PNG offers fallback to single image display for PNG decoders that do not support a PNG. However, neither of these formats is currently widely supported. APNG is supported on Firefox 3.0 and up, Pale Moon, all versions, and Opera 9.5. But since Opera changed its layout engine to Blink, support was dropped. The latest version of Safari on iOS 8 and Safari 8 for OS X, Yosemite, support APNG. Chromium 59.0 has added APNG support. Then Opera added back in 46.0. The PNG group decided in April 2007 not to embrace APNG. Several alternatives were under discussion: ANG, ANIM/MPNG, PNG in GIF, and its subset RGBA in GIF. Examples. Structure of a very simple PNG file. And we have 4 boxes. You could call them columns, I guess, but it's only a one-dimensional array of boxes here, or a one-dimensional array of cells. In the first cell, we have PNG signature. We have 8954E, 47, 0D, 0A, 1A, 0A. And those are the actual byte values, if I understand correctly. In the next cell, we have IHDR, labeled image header below. Then we have a chunk type IDAT, labeled below image data. Lastly, we have the chunk type IEND, IEND, labeled image end. So I believe you can have as many image data chunks as you want, but once you hit the IEND chunk, you are no longer allowed to have the IDAT chunks, and if you have any IData chunks that are coming after the IEND chunk, then your PNG file is malformed, from my understanding. The diagram below has the equivalent hex dump of the 4 cells I just went over. In red is the .png header. The first 4 bytes actually spell out PNG, .png in ASCII. The green chunk has a chunk length of 13 bytes, because 0D in hex converted to decimal is 13. Then we have the letters IHDR in our hex to declare that it's an IHDR chunk, and then the remaining bytes. And I'm not sure why this is not 13 bytes, because the chunk length is 13. There's obviously an aspect of the PNG format here that I'm not quite understanding yet. After that, we have this purple section with a chunk length of 12, because we have that last byte, that's 0C. Remember that chunk length is encoded in 4 bytes. The next 4 bytes is this chunk type here, which is IDANT. I don't actually know hexadecimal ASCII off the top of my head. I'm just reading the hex dump here. After that, the last chunk has a chunk length of 0, and that's the IEND chunk, which makes sense, right? Because it's just saying that there's no more data, so it's kind of like a line ending character in a way. So let's go over the hexadecimal for each chunk type. So before we get to chunk type, we have the header. So .png is going to be 8954E47 in hex. Then our IHDR chunk type is 49484452. The IDAT chunk is 49444154, and the IEND chunk is 49454E44, and those are hexadecimal. That's not decimal, it's hexadecimal. Advantages. Reasons to use this international standard may be: bullet point, portability. Transmission is independent of the software and hardware platform. Bullet point, completeness. It's possible to represent true color, index color, and grayscale images. Bullet point. Coding and decoding in series. Allows to generate and read data streams in series. That is, the format of the data stream is used for the generation and visualization of images at the moment through serial communication. Bullet point. Progressive presentation. To be able to transmit data flows that are initially an approximation of the entire image and progressively they improve as the data flow is received. Bullet point. Soundness to transmission errors. Detects the transmission errors of the data stream correctly. Bullet point. Losslessness. No loss. Filtering and compression preserve all information. And I've actually done this plenty of times to know this is absolutely true. A proper PNG implementation, you can actually create your own bit-packed formats, your own binary formats, and encode the binary into pixels of a PNG file, and then just save it off. And as long as your PNG encoder and decoder are correctly written, you can use that as a binary file format. Flash, Macromedia Flash back in the day, had a bug in their PNG implementation that they never fixed, where 255 could never be represented. I don't know why, but you could just never get 255, and that created problems for me. Bullet point. Efficiency. Any progressive image presentation, compression, and filtering seeks efficient decoding and presentation. Bullet point. Compression. Images can be compressed efficiently and consistently. Bullet point. Easiness. The implementation of the standard is easy. That is a very relative statement there, because I will tell you, I'm still reading through LZW compression and decompression, and it's much more advanced than things I've coded previously. This is an order of magnitude more difficult than anything you will ever do in business programming or web development. Easiness, huh? I mean, yeah, if you're like one of the genius programmers who, came up with this. I don't know. Easiness is all relative to what you already know and your mental capacity. So, take that one with a grain of salt. Bullet point. Interchangeability. Any PNG decoder that follows the standards can read all PNG data streams. Bullet point. Flexibility. Allows future extensions and private editions without affecting the previous point. Bullet point. Freedom of legal restrictions. The algorithm used are free and accessible. In other words, patent trolls won't come after you and try to sue the pants off of you after you worked really hard to build something. And, oh, what do you know? You're using a patent. Maybe that patent isn't as, quote-unquote, obvious and original as the patent office has declared it. Just a thought. Comparison with other file formats. Main article, comparison of graphics file formats. Graphics interchange format, GIF. Bullet point. On small images, GIF can achieve greater compression than PNG. See the section on file size below. Bullet point. On most images, except for the above case, a GIF file has a larger size than an indexed PNG image. Bullet point. PNG gives a much wider range of transparency options than GIF, including alpha channel transparency. Bullet point. Whereas GIF is limited to 8-bit indexed color, PNG gives a much wider range of color depths, including 24-bit, 8 bits per channel, and 48-bit, 16 bits per channel, true color, allowing for greater color compression, smoother fades, etc. When an alpha channel is added, up to 64 bits per pixel before compression are possible. So 64 bits is 8 times 8, which is 64. So that is R, G, B, and A bytes, 4-byte color, or 64-bit color, whatever you want to call it. That is what OpenGL uses. So if you need images to load into a texture in OpenGL, you need the format of the bytes to be R, G, B, and A. Bullet point. When converting an image from the PNG format to GIF, the image quality may suffer due to posterization if the PNG image has more than 256 colors. Bullet point. GIF intrinsically supports animated images. PNG supports animation only via unofficial extensions. See the section on animation above. PNG images are less widely supported by older browsers. In particular, IE6 has limited support for PNG. And just don't use Internet Explorer, even though they seem to have forced it onto Windows computers, and it is impossible to uninstall from a Windows computer. Yeah, so the browser wars, I guess, are still here. JPEG. The JPEG, open paren, Joint Photographic Experts Group, close paren, format can produce a smaller file than PNG for photographic and photo-like images. Since JPEG uses a lossy encoding method specifically designed for photographic image data, which is typically dominated by soft, low-contrast transitions, and an amount of noise or similar irregular structures. Using PNG instead of a high-quality JPEG for such images would result in a large increase in file size with negligible gain in quality. Let's pause to adjust the diagram to the left. It appears to be a visual diff of an image, where on the left side of the divider bar we have JPEG, on the right side we have PNG. The description. Composite image comparing lossy compression in JPEG with lossless compression in PNG. The JPEG artifacts can be easily visible in the background of this kind of image data, where the PNG image has solid color. In comparison, when storing images that contain text, line art, or graphics, images with sharp transition, and large areas of solid color, the PNG format can compress image data more than JPEG can. Additionally, PNG is lossless, while JPEG produces visual artifacts around high contrast areas. Such artifacts depend on the settings used in the JPEG compression. They can be quite noticeable when a low quality, high compression setting is used, where an image contains both sharp transitions and photographic parts. A choice must be made between the two effects. JPEG does not support transparency. JPEG's lossy compression also suffers from generation loss, where repeatedly decoding and re-encoding an image to save it again causes a loss of information each time, degrading the image. This does not happen with repeating viewing or copying, but only if the file is edited and saved over again. Because PNG is lossless, it is suitable for storing images to be edited. While PNG is reasonably efficient when compressing photographic images, there are lossless compression formats designed specifically for photographic images. Lossless WebP and Adobe DNG Digital Negative, for example. However, these formats are either not widely supported or they are proprietary. Don't use them or you'll get sued. An image can be stored losslessly and converted to JPEG format only for distribution, so that there is no generation loss. Quick intermission here. So here's an example of generation loss I found on YouTube. So we save it 1,000 times and it ends up kind of turning into this, which actually isn't too bad compared to this. But notice that in this video they're applying transformations to the image before they save over it. So it looks like the combination of, editing an image a little bit and then saving over it is pretty disastrous to the effects you'll get from generation loss, because it looks like this has totally devolved into noise. Anyways, there you go. That is generation loss. While the PNG specification does not explicitly include a standard for embedding EXIF image data from sources such as digital cameras, the preferred method for embedding EXIF data in a PNG is to use the non-critical ancillary chunk labeled EXIF, that is lowercase e, capital X, capital I, lowercase f. Early web browsers did not support PNG images. JPEG and GIF were the main image formats. JPEG was commonly used when exporting images containing gradients for web pages, because of GIF's limited color depth. However, JPEG compression causes a gradient to blur slightly. A PNG format reproduces a gradient as accurately as possible for a given bit depth, while keeping the file size small. PNG became the optimal choice for small gradient images as web browsers' support for the format improved. No images at all are needed to display gradients in modern web browsers, as gradients can be created using CSS. JPEG-LS. JPEG-LS is an image format by the Joint Photographic Experts Group. Though far less widely known and supported than the lossy JPEG format discussed above, it is directly comparable with PNG, and has a standard set of test images. On the Waterloo Repertoire color set, a standard set of test images, unrelated to the JPEG-LS conformance test set, JPEG-LS generally performs better than PNG, by 10 to 15%. But on some images, PNG performs substantially better, on the order of 50 to 75%. Thus, if both of these formats are options, and file size is an important criterion, they should both be considered depending on the image. TIFF, Tagged Image File Format, within parentheses TIFF, is a format that incorporates an extremely wide range of options. While this makes TIFF useful as a generic format for interchange between professional image editing applications, it makes adding support for it to applications a much bigger task, and so it has little support in applications not concerned with image manipulation, such as web browsers. The high-level extensibility also means that most applications provide only a subset of possible features, potentially creating user confusion and compatibility issues. The most common general-purpose lossless compression algorithm used with TIFF is Lempel-Ziv-Welch, LZW. This compression technique, also used in GIF, was covered by patents until 2003. TIFF also supports the compression algorithm PNG uses, i.e. compression tag 0008 base 16? Adobe style, with medium usage and support by applications. TIFF also offers special-purpose lossless compression algorithms like CCITT Group IV, which can compress bi-level images, e.g. faxes or black and white text, better than PNG's compression algorithm. PNG supports non-premultiplied alpha only, whereas TIFF also supports associated premultiplied data. Alright, so that paragraph was a little bit confusing, because my understanding from what I've read is that PNG uses LZW compression, and this is saying, oh no it doesn't, it uses compression tag 0008 base 16 Adobe style. That makes no sense to me. I don't know if that's a legal thing and it's like actually LZW, but they just named it something and changed a few things. Right, like I believe when I was looking at the source code for puff.c, it did say, like, write your algorithm exactly this way or you might get sued for patent infringement. So maybe that's what's going on here. I'm not sure. Software support. The official reference implementation of the PNG format is the programming library libpng. It is published as free software under the terms of a permissive free software license. Therefore, it is usually found as an important system library in free operating systems. Bitmap graphics editor support for PNG. Main article, comparison of raster graphics editors. A note here, I'm about to read this paragraph word for word, and you might hear something that does not sound correct and sounds like it is bad English. but I am reading it as it is written. It is not me. The PNG format is widely supported by graphics programs, including Adobe Photoshop, Corel's Photo Paint and Paint Shop Pro, the GIMP, Graphics Converter, Helicon Filter, ImageMagick, Inkscape, iFranView, Pixel Image Editor, Paint.net, and Zara Photo and Graphic Designer, and many others. Some programs bundled with popular operating systems which support PNG include Microsoft's Paint and Apple's Photos/iPhoto and Preview, and the GIMP is often being bundled with popular Linux distributions. Adobe Fireworks, formerly by Macromedia, uses PNG as its native file format, allowing other image editors and preview utilities to view the flattened image. However, Fireworks by default also stores metadata for layers, animation, vector data, text, and effects. Such files should not be distributed directly. Fireworks can instead export the image as an optimized PNG without the extra metadata for use on web pages, etc. Web browser support for PNG. Main article, web browser image format support. PNG support first appeared in Internet Explorer 4.0b1, 32-bit only for NT, and in Netscape 4.04. Despite calls by the Free Software Foundation and the World Wide Web Consortium, W3C, tools such as GIF to PNG, and campaigns such as Burn All GIFs, PNG adoption on websites was fairly slow due to late and buggy support in Internet Explorer, particularly regarding transparency. PNG-compatible browsers include Apple Safari, Google Chrome, Mozilla Firefox, Opera, Camino, Internet Explorer 7, still numerous issues, Internet Explorer 8, still some issues, Internet Explorer 9, and many others. For the complete comparison, see Comparison of Web Browsers, Image Format Support. And just a public service announcement, don't use Internet Explorer. In fact, if you're a programmer, don't even work for people who use Internet Explorer. Just don't. Especially versions of Internet Explorer Windows below 9.0 have numerous problems which prevent it from correctly rendering PNG images. Bullet point, 4.0 crashes on large PNG chunks. Bullet point, 4.0 does not include the functionality to view .png files, but there is a registry fix. Bullet point, 5.0 and 5.01 have broken object support. Bullet point, 5.01 prints palette images with black or dark gray backgrounds under Windows 98 and sometimes with radically altered colors. Bullet point, 6.0 fails to display PNG images of 4097 or 4098 bytes in size. 6.0 cannot open a PNG file that contains one or more zero-length IDAT chunks. This issue was fixed in Security Update 947864 within parentheses MS08-024. For more information, see this article in the Microsoft Knowledge Base, 947864, MS08-024, Cumulative Security Update for Internet Explorer. 6.0 sometimes completely loses ability to display PNGs, but there are various fixes. 6.0 and below have broken alpha channel transparency support, will display the default background color instead. 7.0 and below cannot combine 8-bit alpha transparency and element opacity without filling particularly transparent sections with black. Let's read that again with the stuff in parentheses. 7.0 and below cannot combine 8-bit alpha transparency and element opacity, CSS-filter : alpha open paren opacity equals XX close paren, without filling particularly transparent sections with black. 8.0 and below have inconsistent / broken gamma support. 8.0 and below don't have color correction support. Operating system support for PNG icons. PNG icons have been supported in most distributions of Linux since at least 1999, in desktop environments such as GNOME. In 2006, Microsoft Windows support for PNG icons was introduced in Windows Vista. PNG icons are supported in Amiga OS 4, AROS, Mac OS, iOS, and Morph OS as well. In addition, Android makes extensive use of PNGs.